Welcome everyone to this session where we'll delve into a classic physics problem, determining the speed of sound in air using resonance. This experiment is fundamental to understanding wave phenomena, which is crucial in fields like acoustics and the design of musical instruments. Let's begin by visualizing our setup. Imagine a tall, narrow tube partially filled with water. A tuning fork is held just above the open end of the tube. When the tuning fork vibrates, it sends sound waves down the air column. These waves reflect off the water surface, which acts as a closed end. When the length of the air column is just right, a standing wave forms, causing the sound to resonate loudly. Now, let's identify our key variables and constants. First, we have the frequency of the tuning fork, which is the source of our sound waves. We'll denote this as f. Its value is given as 500 Hz. Next, we have the lengths of the air column at which resonance occurs. These are the distances from the top of the tube to the water level. We'll call these L values. We are given 4 resonance lengths. L1 equals 16.0 centimeters, L2 equals 50.5 centimeters, L3 equals 85.0 centimeters, and L4 equals 119.5 centimeters. Our goal is to find the speed of sound in air, which we'll represent as v. The principle at play here is resonance in a tube closed at one end and open at the other. For such a tube, resonance occurs when the length of the air column is an odd multiple of a quarter wavelength. This means the fundamental resonance corresponds to 1/4 wavelength, the next to 3/4, then 5/4, and so on. A crucial insight is that the distance between any 2 consecutive resonance lengths in such a tube is exactly half a wavelength. We can express this as the difference between successive lengths, like L2 minus L1, being equal to lambda over 2, or lambda over 2. Once we find the wavelength lambda, we can calculate the speed of sound using the fundamental wave equation. V equals f multiplied by lambda. Let's perform the calculations. We'll find a difference between successive resonance lengths. L2 minus L1 is 50.5 centimeters minus 16.0 centimeters, which gives 34.5 centimeters. L3 minus L2 is 85.0 centimeters minus 50.5 centimeters, also 34.5 centimeters. And L4 minus L3 is 119.5 centimeters minus 85.0 centimeters, again, 34.5 centimeters. The consistency of these differences confirms that 34.5 centimeters represents half a wavelength, lambda over 2. Therefore, the wavelength lambda is 2 times 34.5 centimeters, which equals 69.0 centimeters. To use this in our speed calculation, we to meters, 0.690 meters. Now, we can find the speed of sound, v, using v equals f times lambda. V equals 500 Hz multiplied by 0.690 meters. This calculates to 345 meters per second. To check our answer, we compare it with typical values. The speed of sound in air at room temperature is generally around 343 meters per second. Our calculated value of 345 meters per second is very close and well within the expected range for such an experiment, which gives us high confidence in our result. In conclusion, by observing the resonant lengths in a tube with a tuning fork, we've determined the speed of sound in air to be 345 meters per second. This method is incredibly valuable as it allows us to measure wave properties directly. Understanding resonance and wave speed is fundamental not only in physics, but also in engineering applications like acoustic design for concert halls, ultrasound imaging in medicine, and even the functioning of musical instruments like flutes and organ pipes. A significant advantage of this method, using the difference between successive resonances, is that it naturally accounts for what's known as the end correction at the open end of the tube. We don't need to explicitly calculate it, as it cancels out when we take the difference, allowing for a more accurate determination of the wavelength. So the key takeaway here is that by carefully measuring the lengths at which sound waves resonate, we can deduce the wavelength, and then, using the known frequency of the source, precisely calculate the speed at which sound travels. This problem beautifully connects concepts of wave motion, resonance, and practical measurement. Thank you for joining me for this problem-solving session. If you found this explanation helpful, please consider liking this video, subscribing to the channel for more physics and mathematics content, and sharing it with your friends. Feel free to leave any questions or comments below. And if you have a specific problem you'd like to see solved, consider making a donation to the channel. Each month, we'll select a few donor-requested problems to solve in their own dedicated video.